What specific problem does your proposed method aim to solve in the context of 3D generative AI, and why is this problem significant for developers in creating Roblox experiences?
Our proposed method aims to solve the challenge of effectively representing and generating 3D geometry from multimodal inputs, which is crucial given the limited availability of 3D training data compared to other modalities like text and images. This problem is significant for developers creating Roblox experiences because it enables them to generate complex 3D objects, scenes, and interactions from simple text prompts, thereby streamlining the development process. By utilizing a discrete tokenization scheme for 3D shapes, our model allows for the generation of high-quality 3D assets that can capture intricate geometric details, which are essential for immersive experiences. Additionally, the ability to collaborate with existing large language models enhances the model's utility, allowing developers to leverage common-sense knowledge and reasoning capabilities in their designs. Ultimately, addressing this problem empowers developers to create richer and more engaging 3D environments in Roblox.
How does the proposed algorithm work? Please illustrate the methodology step by step, including the role of the tokenization scheme and the transformations applied to the 3D shapes.
The proposed algorithm for 3D shape generation involves several key steps, primarily centered around a discrete tokenization scheme. First, the algorithm begins by encoding a 3D shape into a continuous latent vector using a transformer-based architecture, which captures the geometric properties of the shape. This continuous representation is then transformed into discrete tokens through a vector quantization (VQ) process, specifically utilizing an optimal transport VQ variant to stabilize training and improve gradient flow. Next, the tokenization scheme allows for the generation of shape tokens from text prompts in a text-to-shape application where a decoder-only transformer generates these tokens autoregressively, conditioned on the input text. Additionally, the shape-to-text application encodes the 3D shape into shape tokens, which are then processed by a pre-trained language model to produce descriptive captions. This dual tokenization approach facilitates seamless collaboration between the text and shape modalities, enabling applications like text-to-scene generation, where the generated shapes can be integrated into larger 3D environments. Overall, the methodology emphasizes the importance of the tokenization scheme in bridging the gap between textual and geometric representations, enhancing the model's ability to generate and manipulate 3D content effectively.
Can you provide a simple yet illustrative example that demonstrates the inner workings of your algorithm, specifically detailing the step-by-step process from input text to generated shape?
To illustrate the inner workings of our algorithm, consider the example of generating a 3D shape from the input text prompt, a motorbike with wings. The process begins with encoding the text prompt using a pre-trained text encoder, which transforms the input into a format suitable for the model. Next, this encoded text is fed into a decoder-only transformer architecture, similar to GPT-2, where dual-stream attention is employed to integrate the text conditioning into the generation process. The model then autoregressively outputs discrete shape tokens that represent the geometry of the motorbike with wings. Finally, these shape tokens are processed through a mesh extraction algorithm, such as marching cubes, to create a triangle mesh model that visually represents the described object, completing the transformation from text to a 3D shape.
What are the theoretical and practical benefits of using your method compared to existing alternatives in creating 3D models, especially in terms of efficiency, accuracy, and user collaboration?
The theoretical benefits of our method, particularly the discrete shape tokenization, lie in its ability to effectively capture a wide range of geometric properties while enabling seamless multimodal interactions. This approach allows for efficient collaboration with users by accommodating various input modalities, such as text and images, which enhances user experience and creativity. Practically, our architecture demonstrates improved accuracy in shape reconstruction, as evidenced by superior surface IOU and volumetric IOU metrics compared to existing alternatives like Craftsman. Additionally, the autoregressive nature of our model allows it to handle unbounded input-output sizes, making it adaptable to diverse 3D scene complexities. Overall, our method not only streamlines the 3D modeling process, but also fosters a more intuitive and collaborative environment for users, leveraging the strengths of both AI and human creativity.
How did you validate your proposed method? Please explain the experimental design, datasets used, performance metrics, and how these demonstrate the method's effectiveness.
To validate our proposed method, we conducted experiments comparing our discrete shape tokenizer against a continuous variant and Craftsman, a recent model trained on a smaller dataset. We utilized a training dataset comprising approximately 1.5 million 3D object assets, which included both licensed and publicly available datasets, ensuring a diverse range of 3D shapes. The performance metrics employed for evaluation were surface IOU, SIOU, and volumetric IOU, VIOU, which measure shape reconstruction quality by assessing the accuracy of the generated shapes against ground truth. Our results indicated that both our VQ-VAE, ours VQ, and the continuous variant, ours KL, outperformed Craftsman in both SIOU and VIOU metrics, demonstrating the effectiveness of our approach. Although the continuous variant showed superior performance, highlighting some loss of geometry fidelity in the discrete variant, we aim to address this gap in future work, indicating a clear path for improvement and validation of our method's potential.
What specific results were achieved with your new method, particularly in comparison to other existing methods, in terms of shape reconstruction quality and fidelity?
Our new method, specifically the discrete shape tokenizer, demonstrated superior shape reconstruction quality compared to existing methods, particularly Craftsman, as evidenced by our evaluations using surface IOU, SIOU, and volumetric IOU, VIOU metrics on the TOYS 4K dataset. Both our VQ-VAE, ours VQ, and the continuous variant, ours KL, outperformed Craftsman in these metrics, indicating a significant improvement in capturing geometric fidelity. However, while the continuous variant still surpassed its discrete counterpart, it highlighted a loss of geometry fidelity through the vector quantization process. We aim to address this gap in future work, indicating that while our method is effective, there is still room for enhancement in the discrete tokenization approach. Overall, our results suggest that our method approaches the visual quality of state-of-the-art techniques based on continuous latents, such as Trellis and Hunyuan 3D2, while also supporting multimodal tokens.